All right. Yeah, there's only a few of us here, but we're going to start the next packet, and but we'll take it slow, and then we can do some recap tomorrow. But let me start off with the calendar, kind of give you an idea of what is coming up. So if you flip to the second page there, you'll see the calendar. I think a lot of it is kind of the same from the last calendar you had. So we're going to, our focus with this new packet is going to be particle motion and Riemann sums. We're also going to do some antiderivative word problem, the rate in, rate out problems. It's in the packet, but it won't be on the quiz next week. Next week will be our FRQ quiz. It'll just be 2 problems, 1 particle motion and 1 Riemann sum. So we'll have plenty of time to review. So today we're just going to try to get through pages 1 and 2. And then tomorrow I'll do a little bit of recap with 1 and 2, and then but we'll move on to 3 through 6. But you know, we're just covering 2 topics, and you've already seen the topics, so a lot of it is just review. So we'll do that today. After that, next Wednesday, we're going to start our multiple choice review. So multiple choice will be split up into 2 days. Be Tuesday and next Tuesday after next, and then Friday. Both of these will be 30 minutes, 30-minute periods. Well, actually, this may be a longer period. This more like 40 minutes, and this will probably be the full hour, but I'll make both of these 30-minute portions, but you can take a little bit longer if you need to. So the first test will be just first semester topics, so derivatives, which we're going to cover through our packet. And then we'll review second semester topics starting maybe Monday, but we can do that Wednesday and Thursday, and then you'll take your second portion on Friday. And that brings us to the end of end of April. And then we'll have 2 weeks in May before we get to our AP exam. So this week we'll focus on FRQ packet, which we'll do in class, and then whatever you don't finish, you finish in class, finish at home for homework, but this will count towards a quiz grade just for completion. And then May 6th through 10th, we'll work on multiple choice packets, packet number 6, multiple choice packet, and then whatever we do, whatever you don't finish in class, you can do for homework. But this one, there will be no late penalty. So you can turn it in anytime after the AP exam, after the 13th. So I am going to check the FRQ pages on a daily basis, but I know a lot of students will be out on 6th to 10th, so I'm not going to have any late penalty for homework, but you're going to be working on that at home, and then you can turn it anytime after that. Both packets 5 and 6 will be counting towards a quiz grade. So there's 2 individual quiz grades between packets 5 and 6.
How's it going to work for seniors? Because I know the last day senior year is like before the exam, but
yeah, that's true. So I mean, if I think maybe the 10th. So I think if grades are due sometime here, I think I can push it out where if seniors turn in their homework or packet, I mean, I'll give you packets 5 and 6 before May, so you can work on it. And if you're not going to be in school at all this week, then you can send me the pages, or you can bring it to me sometime later. Right. Okay. Any questions with our calendar? So we have 4 grades remaining. We have a quiz Tuesday. Next Tuesday, we have multiple choice tests broken up into 2 days, and then we have 2 quiz grades. But the final 2 quiz grades are just going to be we're treated like homework, but we're just be doing it for completion. Good. All right, page 1. All right. Number one, a car travels on the straight track. During the time interval from 0 to 60 seconds, the car's velocity v, measured in feet per second, and acceleration a, measured in feet per second, are continuous functions. Okay? So there are no breaks anywhere, even though we're only told the velocity acceleration at these time intervals. We know there's nothing strange going on between these times. It's all both velocity and acceleration will be continuous. The table above shows selected values for these functions. So let me just walk through some of this table here. So at 0 seconds, velocity is -20, acceleration is +1, 15 seconds, 25 seconds, 50 seconds, velocity is 0, and at 60 seconds, velocity is 10. What do you think is happening? This car's traveling along a straight track here. What do you think this negative to 0 to positive? What is that? Can that give you an idea in terms of visually what's happening with this car?
It's positively accelerating.
Okay. What do you think this negative velocity means?
It's going to the left.
Yeah, it's going left. So it's on a straight track. It's either moving left or right. This is going left, and then what's happening here at 50 seconds?
It's turning around going.
Yeah, good. It's turning around. So the fact that when it turns around and moves the other direction, it's got to stop, and so that's what's stopping here. So stopping at 50 seconds, and then after that, it's moving to the right. It doesn't mean that it's immediately moving to the right afterwards. It could stop and then continue moving left and then stop again and then move to the right. But we know that somewhere along this interval, it's got to change direction. It may not change direction right at 50 because a lot of things could happen in the next between 50 and 60 seconds that we don't know about, but we know that there's got to be a change in direction somewhere between here.
Shouldn't the acceleration be negative, like as because it's going to the left with like a decreasing rate?
Well, it's possible for acceleration to still be positive even when it's going left. But yes, if these signs are opposite, that means it's slowing down.
Okay.
Right. If the signs are the same, that means it's speeding up. Yeah. Okay, so using appropriate units, explain the meaning of the definite integral from 10 to 60 of absolute value of velocity in terms of the car's motion. Approximate the integral from 30 to 60 absolute value of v of t using a trapezoidal approximation with 3 subintervals determined by the table. So what do you think the accumulation or the integral of velocity is going to give us? Look at some of these formulas here. Does any of these look like the ones that we are working on? What is the integral of velocity going to give us? Okay, how about this one here? What's that?
Gives total distance.
Total distance, yeah. So if we're accumulating velocity over a period of time and we're only looking at the absolute value of velocity, that means it's total distance. That means regardless of moving left or right, we're going to be able to gather exactly how much the car is going to move. So if it's moving left, we're going to accumulate that car's distance. If it's moving right, we're also, it's like a odometer where it doesn't matter which direction the car is moving, it's going to continually gain miles, right? Okay, so we know it's a distance, total distance traveled between 30 to 60 seconds. So we can write that down. So now we're going to use a trapezoid approximation to figure out roughly how much distance does this car travel in the 30 seconds. So we have a formula for trapezoid. I'm going to memorize. But multiple variations of this, you can do 1/2 with height 1 plus height 2. Or width over 2, height 1 plus height 2. Okay, so between 30 and 60 seconds. Remember how we do Riemann sums or interval area approximation, right? We're going from 30 to 60, so within each block, we can subtract the values to figure out the width, and then the height, we're going to use the velocity values, height 1 plus height 2, height 1 plus height 2, but we're going to keep these negatives, right? So now we're going to keep these negatives before. I'm sorry. We're going to make them what? This is absolute value here. So we're going to make all these what? Positive. Yeah, sorry about that. Yeah, if it was displacement, then we would keep it negative, but because we're doing distance and the absolute value is there, we're going to convert all those negative velocities to positive velocities. Okay, so we do 3 trapezoids. So width over 2. First width is 5 over 2, height 1 plus height 2. Width over 2, height 1 plus height 2, and then width over 2, height 1 plus height 2. Okay, next part B. Using appropriate units, explain the meaning of the depth integral from 0 to 30 of the of A of t. Okay, what do you think the integral of acceleration is going to give us? Velocity, yeah. So this is first theorem, right? So first theorem says the integral of A of t is going to become what? From A to B is going to be V of B minus V of A, yeah. So part B, we're using first theorem here, application of that. We know the integral from A to B of A of t. Acceleration is going to turn into velocity because of the integral. Integral is going to change what's happening with that acceleration. And it's going to be V of B minus V of A. Right, there's all these different variations of first theorem. Velocity will rise up to position. Acceleration rises up to velocity. F prime rises up to F. F double prime rises up to F prime. So the integral is always going to push this to a function above it, right? One level above it, 1 degree above it. So if we apply it in this form, we know the integral from 0 to 30 of A of t. It's just V of 30, sorry, minus V of 0. Okay, can we describe now? We can replace these with numbers, right, and get the number value, which we're going to do. But the more important thing is, it says explain the meaning of this. What does V of 30 minus V of 0 mean? If you were to describe what this number is giving us in return. Yeah, what is the V of 30 minus V of 0? What does this mean?
Changing direction. Sorry.
Not changing what?
Loss.
Change of velocity, right? So if we know the velocity, if we know the car's velocity at 30 seconds, and if we know the car's velocity at 0 seconds, and we subtract it, then it's just the change in velocity in that 30 seconds.
How do you displacement?
I'm sorry?
It's displacement, right?
No, displacement would be x of 30 minus x of 0, right? Change in position would be displacement. If it's change in velocity, there's no name for it. We just say change in velocity, yeah. So cars change in velocity in the 30 seconds from 0 to 30, and then we just find what is that change in velocity. So the velocity at 30 seconds is -14. The velocity at 0 is -20. The difference between them is going to be 6 feet per second. So in the time period between 0 and 30 seconds, this car's velocity is going to change 6 feet per second. Part C, must there be a time when velocity is -5? So looking at this, can we guarantee that there's going to be a time when velocity is going to be equal to -5? I mean, we don't see -5 show up in our velocity table, but can we guarantee that there will be a -5 somewhere that's going to be between 0 and 60? So we go from -20 to -30 to -20 to -14 to -10. -10 to 0.
And just, it has to be a 5.
There's got to be a -5 here, right? I mean, there could be more others that we don't expect, but we know that in order to get from -10 to 0, it's got to pass -5 somewhere, right? And we're told that the velocity is continuous. So do you guys remember what theorem is this? We can guarantee that
Mean value.
close mean values with derivatives. This is going to be
Extreme.
IBT. Yeah, any mean value theorem says that if I have a point below my target and a point above my target, and I know that my my graph is not going to skip, it's going to be continuous all the way through, then we know that whatever middle point we're looking for has got to be guaranteed. So this is the most efficient way, I think, to write it. We can identify the location of our value below our target. We identify a point of a time when velocity is greater than our target, and then we know that whatever's in between has got to be reached. Right. So since v of 35 is -10 and -10 is less than -5 and -5 is less than 0, and 0 is from v of 50, we know between -10 and 0, we know we're going to hit that -5. So there's other ways to write it, but this is the most efficient way because, or less, this is the least wordy way of writing it. IBT guarantees a time t in the time interval from 35 to 50 seconds such that v of t must be equal to -5 in that time interval, at least once, maybe more than once, but we know it's got to pass -5 at least once if we want to go from -10 to 0. Okay, now look at part D here. Between 0 and 60 seconds, must there be a time when acceleration is equal to 0?
No.
Well, maybe not by IVT, right? Because we see 1, 5, 2, 1, 2, 4, 0, 4, 2. If we're just looking at acceleration, we're not going to be able to make that justification, right? Because it's not going to hit 0. But what if we use velocity? Acceleration is the what of velocity?
Change in velocity.
Okay, what's another word?
Pressure.
Derivative, right? And derivative, what's another word for derivative? Slope. So can we find a place where the velocity function is going to experience a slope 0? Well, here's the thing. This is the hint is between these two here. Okay. So imagine a velocity that hits -20, goes to -30, comes back up to -20. Can we guarantee a slope 0 somewhere along that velocity curve? So imagine this is the velocity graph right here, right? Starts off at -20, and then it goes down to -30, and it comes back up to -20. Okay. What's going to happen to that velocity graph? It's going to experience what? A slope. It's going to flatten out, right? This is what slope what at this point? That's a slope 0, right? So we know that somewhere between velocity is going to have to kind of level off and come back up. And in that time period, we can guarantee acceleration must be 0, even though we don't see it here. Right? And that's Rolle's theorem. Rolle's theorem says, if I can guarantee a slope using my velocity graph, then that slope that I see between the two endpoints must exist on the curve as well. So by Rolle's theorem, since our velocity is continuous on the closed interval and differentiable on the open, and v of 0 and v of 25 is they're both -20, right? If it's starting at -20 and it goes down to -30, it's got to come back up to -20 somewhere between. And then in that process, if my velocity is experiencing a slope 0 of velocity is acceleration equal to 0. Okay, we're just going to do one more and then we'll be done. So let's look at number 2. Okay, so go to page 2. Go ahead and read the problem and see if you can make sense of the steps. See if you can try A and B on your own, and then I'll walk through each of the steps with you. Okay. Temperature of water in the tub and time t is modeled by strictly increasing twice differentiable function. That just means a smooth curve that both the derivative and second derivative are going to be smooth curves. WT is measured in Fahrenheit and T is measured in minutes. At time t equals 0, temperature of the water is 55 degrees. The water is heated for 30 minutes, beginning at time t equals 0. Values of WT for the first 20 minutes are given in the table above. So here, simple to understand what's going on here. At 0 minutes, the temperature in the tub is 55 degrees, and then rise to 57, then 61, then 67, and by 20 minutes in, it's going to have gotten all the way up to 71 degrees. And use data to estimate W prime of 12. Show the computation that leads to your answer. So W prime of 12, this is a derivative notation. Can't do derivative with without a function, but we can do what? What's derivative related to? Another word for derivative. Slope, right? Right. And then what information do we need if we want to gather slope? Yeah. So, okay. So what information would you use? Which table, which values would you use?
Change in degree Fahrenheit or changes in minutes.
Which numbers would you use though? 9 and 15. Why these two? Yeah, good. Closest, right? The closer we are to our target, the better our approximation will be. Right? So we just do change in temperature over change in time. It's not going to be super accurate, but because our table is such limited, we have such limited data, we just have to pick the best option that we have available to us. What do you think the units will be here? Good. Yeah. So if we get a positive, that means our rate is going to be increasing. If we get a negative, that means it's going to be decreasing. So we see between 9 and 15 minutes, our temperature is rising. So our average rate of change is going to be a positive degrees per minute, about 1 degree rise per minute at that 12th minute. Part B, use the data and table to evaluate the definite integral from 0 to 20 of W prime of T dt. Using correct units, interpret the meaning of the definite integral from 0 to 20 of W prime. So W prime integral, what's the integral W prime going to turn itself into? There's also a first theorem. W prime changes to what? Just what? Just W, yeah. So first theorem says the integral notation is going to change the nature of the function. Going to make it rise to a different level. So F prime rises up to F. So W prime will rise up to W. So this is W20 minus W0. How would you interpret that? What is W20 minus W0? What information is that giving us? Okay. And something else though. Yeah, that's right. Change in temperature. In this case, it'll be rise. Yeah. So it's a change in temperature between the 0 and 20th minute. And because the temperature rises 16 degrees, we can say the temperature is going to increase over the course of over the 20-minute interval, 16 degrees. Part C, the average temperature is given in this interval, formula 1/20th integral from 0 to 20 of WT dt. Use left Riemann sum to estimate to approximate the value of 1/20th integral from 0 to 20 of WT dt. Does this approximation overestimate or underestimate the average temperature? So we'll do the approximation first, and then we can talk about the over and under approximations. So do left Riemann sum. So each subinterval, you can bracket off and subtract the x values or t values to get to your width, and do width times height for each of the subintervals. Don't forget about 1/20th. So the way that I'm getting these numbers, the 4, the 5, the 6, and the 5, simply by using the table of values here, and I'm just subtracting t values, right? 0 and 4, that's 4. 4 to 9, that's a width of 5. 9 to 15, that's a width of 6. 15 to 20, that's a width of 5. And then with each rectangle, we're choosing the left height. So 4 times 55, 5 times 57, 6 times 61, 5 times 67. And we can also conclude that the estimation is an under approximation because we're using area using left Riemann sum. So if you can visualize every rectangle, well, first off, we know our temperature is rising, so we know our graph is going to be increasing, and we know it's strictly increasing. So that means it's not going to suddenly dip because they tell us it's always rising. And if our graph is rising, then our left Riemann sum, if we're attaching the left endpoint of each rectangle to the curve, all of our rectangles are going to sit below the curve. So our area approximation, our temperature approximation is going to be under approximating. We don't have to draw the graph, but the graph helps. But then you do have to say estimation is under approximating because we're using left Riemann sum on an increasing graph. Part D, between 20 and 25 minutes, the function W that models the water temperature is first given by W prime. Based on this model, what is the temperature of the water at time 25? So we can use the formula final equals initial plus displacement. So if we use that formula, then we can say W of B is equal to W of A plus however much the temperature is going to change in that time interval. So if I want to find the 25th minute temperature, I'm going to start at the 20th minute because that's what's given to me. I'm not always starting at 0. I'm always starting at whatever they give me. So that's my anchor point. And then I want to figure out how much change in temperature does the tub experience. And if I can figure out the change in temperature in that 5-minute period, I can add that to the starting temperature at 20 minutes, and I can figure out what the temperature is going to be at the 25th minute. Yeah. Yeah, every school clips separately. Okay, any questions here? So tomorrow, I do want to check your packet 2, page 13 to 16. I think some of us have already shown, if you were here Friday, you would have shown me before break. But packets 1 and 2, those packet checks are going to go towards your FRQ test 1. So I want to make sure I can get those pages checked. So tomorrow I'll send out a reminder this afternoon that I'll be checking those pages. And tomorrow we'll work on pages 3 through 6. You guys already finished pages 1 and 2. So we'll continue working on packet 3 tomorrow. Okay. All right. Thanks, everyone. Come get your phones.
I was in Florida.